Okay, I think we can start. We have some English-speaking guys in the Zoom auditorium, so we'll speak English. I hope everything will be understandable today. So what we did previous time, we derived the kinetic equation describing the conductivity of semiconductors. This is very beginning. Let me skip it. This is the definition of distribution function, the left-hand side of kinetic equation. What we did in the previous lecture, we wrote down the so-called collision integral for the kinetic equation. This is the right-hand side of the equation governing the evolution of distribution function. And this right-hand side shows us the stochastic processes, the processes due to which electron can leave some part of phase space and transfer to another part of phase space due to colliding with some random objects like random impurities or phonons and so on. All the previous lecture was devoted to deriving the collision integral. What is that? We wrote it down from quantum mechanical point of view. We wrote it down for scattering by some object that can be characterized by scattering probability W. And we transformed it. We wrote it as the probability that this part of phase space, this distribution function, is occupied, the final part of phase space characterized by vector r and p prime is not occupied, and some transition probability, and the vice versa processes that lead to backward population of the given volume of the phase space. We transformed it further and simplified it. The simplifications were based on the equality of forward and backward scattering probabilities. Due to this, we have shown that for every elastic process, the Pauli blocking is forgotten in the collision integral, and it is proportional just to the difference of distribution function in the given phase space and in some other phase space p prime, which will be integrated. We recalled that the scattering probability can be derived with Fermi golden rule. The Fermi golden rule is very well known from quantum mechanics. This is the key result of time-dependent perturbation theory, which links the probability of scattering to the interaction matrix element between initial and final states. And there is some delta function governing the energy conservation law. Just to refill your attention, I would like to ask the following question. You see that there is some delta function in the expression for the scattering probability per unit time. Delta function is some pathological objects in mathematics because it's infinite at one point where energies are equal, but it is zero at all other points. How do you think? Will the results obtained with Fermi golden rule and the collision integral will be so pathological in mathematical sense? Can we get some normal results with this delta function? What is your idea?
When we will integrate with in momentum space, this delta function will be cancelled out.
Yes, this is the great answer. This, of course, the probability to transfer from this point of phase space to another point of phase space is singular. It contains this bad delta function. But if we recall that collision integral is collect the information from all points of the space, this integral cancels this singularity, and the results we will obtain further will be very good and non-pathological. They will be physical. Okay, let's go further. What we did Further, we applied the kinetic equation to the calculation of conductivity in a semiconductor. If the distribution function is simply the Fermi function, equilibrium Fermi function, which has circular contour in, which has a circle in the momentum space. This is not, well, let's try this. If the distribution function is a circle in momentum space, like it always happens in equilibrium, this state carries no current. Because what is current? Current is average velocity carried by all the electrons. But for every forward electron, we have an equivalent backward electron. So if the distribution function is equilibrium function, then there is no current. And we solve this equation by successive approximations. We assume that there is some equilibrium part of distribution function plus small amendment, which is proportional to the electric force. And the main effort during the previous lecture was devoted to simplifying the collision integral. And the collision integral was greatly simplified in the so-called tau approximation. Well, we have written a lot, but the key result was that all this terrible term with the collision integral can be cast in a very simple form. Minus delta distribution function divided by some characteristic time, which we denoted by tau p. And the meaning of that is the momentum relaxation time. Its formal expression is very simple and great. This is the integral over phase space of transition probability per unit time, which contains this delta function, and multiplied by 1 minus cosine of scattering angle. The meaning of cosine was explained, and we have learned that if the particle is deflecting at small angle during the scattering, then it doesn't lead to relaxation of velocity and doesn't lead to relaxation of current, and therefore these collisions are unimportant for conductivity. And therefore this should be ignored, and the 1 minus cosine factor does this work. It ignores the small angle collisions, because when scattering angle turns to 0, then this factor turns to 0, and collision frequency doesn't know about that. So what was what we did finally? We wrote a formal expression for the conductivity. We solved the kinetic equation in the tau approximation. We found the amendment to distribution function caused by the field. It was really anisotropic. It looked like an ellipse, and therefore it carried some finite current. And this current became proportional to the electric field. And the proportionality coefficient was nothing but the conductivity. What was the home task? The home task actually was to calculate the conductivity of semiconductor up to, or metal up to an end. So if the momentum relaxation time is proportional to momentum to some power alpha, what would be the conductivity? Because why this question has arisen? This is because the expression for the conductivity we have obtained doesn't look very much like the Drude formula. We got used to a Drude formula that sigma equals ne squared tau divided by m, where n is the electron density, m is the effective mass, tau is some relaxation time. This doesn't look like this, and maybe it should be somehow transformed to this form. Did someone do the home task? Did someone manage to do it? Did some of you attempt to do this and get some questions? Okay, if no one attempted, then I will try to obtain this result in the case of metal. Metal is the state of matter that is characterized by distribution function with high Fermi energy compared to the thermal energy. So the distribution function will be something like a step function. And I will try to prove that the Drude formula, at least for 3D metals, can be restored independent of specific form of tau p. I would try to do it in the most quick way. So our formula for conductivity is the elementary charge squared divided by the dimensionality of object, 3 for three-dimensional piece of metal. This is the integral over energies of density of states function squared carrier velocity, derivative of equilibrium distribution function with respect to energy, and momentum relaxation time depending on energy itself. The main simplification that we will use is that the derivative of equilibrium distribution function is approximately the delta function. Is it clear for you or not so much? Do you have any misunderstandings about that?
So we have Fermi function as a step, and then we find
Yes, of course. Yes, this is true, because Fermi function is looking like a step-like function. Approximately. It is slightly smeared, but approximately it is a step. The derivative of a step is minus delta. If we plot the derivative of this, f prime with respect to energy, this would look like a pump at the Fermi level. So to mimic this pump, we write it as a minus delta function at the Fermi level. Right? Or any question? Okay, then due to this, when calculating the integral, we can approximately evaluate all the quantities at the Fermi level, because the Fermi function is sharp. So I will, and as these are roughly constants, then I will try to factor it out of the integration sign, because these can be treated approximately as constants. Then I would like to use the following simplification. It is minus e squared divided by dimensionality of space. Fermi, the carrier velocity at the Fermi level is nothing but Fermi velocity squared, and this is the momentum relaxation time evaluated at the Fermi level. What we get as a remainder is the integral over the energies of the density of states and derivative of Fermi function. But the following trick will be almost exact. Let's remember what is Fermi function. It is unity divided by unity plus exponent of energy minus Fermi energy divided by kT. Look, if we differentiate this with respect to energy, this is identical to differentiating this function with respect to minus Fermi energy, because the only possible combination is E minus EF. So the following equality is exact. The derivative of F0 with respect to E is minus derivative of F0 with respect to EF. But EF is treated as constant when evaluating this integral. So we arrive at the following nearly exact statement. It is my E squared divided by D, Fermi velocity squared, tau p evaluated at Fermi energy, and multiplied by derivative of the integral E, density of states, and multiplied by Fermi function. But what is this? what appears here under the integration sign? Can we call this whole entity as with some shorthand notation? Do you recall something from here? Yeah, this is the number of particles. This is the, more precisely, this is the carrier concentration, if the density of states is measured per unit volume. So this is almost a great result. It is E squared divided by dimensionality of space. Let us try to cast this into the form of Fermi energy. Let's multiply by mass and divide by 2. And here you get a 2. And the mass, 2e squared divided by md, Fermi energy, momentum relaxation time at Fermi level, and derivative of particle number with respect to Fermi energy. This is already a better. Now let's consider some more specific case, three-dimensional bulk metal. From the course of the statistical physics, you know how this integral is evaluated. The density is proportional to Fermi energy to the power of 3/2. Therefore, the derivative of density with respect to Fermi energy is 3/2 of density divided by Fermi energy. And what we recall finally, that d is equal to 3. So we exactly arrive at the Drude formula. 2e squared divided by 3 masses, Fermi energy, momentum relaxation time, and 3 divided by 2 density divided by Fermi energy. Fermi energy has cancelled out, these 3/2 have cancelled out, and we get n e squared tau p divided by m. This is how we have justified the Drude formula for the three-dimensional metal. This looks tricky, and this looks quite peculiar because we use the dimensionality of space equals to 3, and we used actually implicitly the parabolicity of electron spectrum, because only due to this n is proportional to the Fermi energy to the power of 3/2. I think it would be a good home task to justify the fact that the Drude formula for metals, n e squared tau p divided by m, works both for 3D and 2D systems. And the spectrum of carriers can be arbitrary. So the energy versus momentum should not necessarily be parabolic. So we have actually assumed that E versus P is a parabolic function, P squared divided by 2m. But there are some other instances like Weyl semimetals and Dirac semimetals that have a linearly dispersive energy versus momentum. And actually most metals like copper, plumbum, or stibium have very weird energy versus momentum dependence, like they cannot even describe by some simple formulas. That for arbitrary spectrum, the Drude formula should work fine. This is a good home task for you. For a while, it can look that we didn't get something new. Do you have any questions, meanwhile, for the conductivity in the case of metals? Don't be shy. Don't be shy. Дарья, вам все понятно? Что? Есть вопросы? Что-нибудь непонятно? Yes, what changes in the case of semiconductors? What changes in the case of semiconductors? Actually, I wanted it to make a home assignment for you, but actually what changes in the case of semiconductor is the shape of the distribution function. The distribution function in the case of semiconductor is of course a Fermi function, but in the conduction band, there is a very limited amount of electrons. Yes, it looks more like a Boltzmann function. So if we plot F0 here somewhere the bottom of the conduction band, this is the energy. The Fermi level is somewhere in the band gap, and in the conduction band we have almost Boltzmann statistics, and therefore as we have to integrate only over the conduction electrons, then we can better approximate the distribution function as exponential. So here F0 is better approximated as exponential of minus p squared divided by m divided by kt plus Fermi level divided by kt. So Fermi level is somewhere here, where the cusp or where the bending of the distribution function changes the sign. So the only difference here is that the distribution function is different. And in this case, the results are not so universal, and proper averaging of momentum relaxation time has to be done. So I think we have time to do this, though I am not sure that we will get an accurate result. Okay, let's denote the characteristic momentum, thermal momentum, as square root of 2m kt. This will be our shorthand notation. Then the distribution function can be cast in a simple form as exponent of minus momentum squared divided by thermal momentum squared and exponent of Fermi level divided by kt. Of course, Fermi level has to be reckoned from the conduction band. So let us do this very accurately. E minus Pc divided by kt. And let us assume that the dependence of momentum relaxation time on momentum itself is a power law dependence. We write just from dimensionality arguments that tau is tau 0 multiplied by p divided by thermal momentum to the power of alpha. And actually we will not obtain Drude formula here in its direct form, but we will obtain Drude formula with some prefactor that can depend on alpha itself. So let us rewrite it up to an end. We remember the derivative of Fermi function. So this is e squared divided by d kt. We remember the spin degeneracy g and integrate over momentum space from 0 to infinity in spherical coordinates for pi momentum squared delta momentum divided by 2ph to the power of 3 for three-dimensional objects. Velocity squared is nothing but momentum squared divided by mass squared, and here we have equilibrium distribution function multiplied by momentum relaxation time, p divided by p0 to the power of alpha. Let us make the change. So I have plugged this here into the definition of momentum relaxation time and use the notation for derivative of distribution function with respect to energy. Any question? kT. What? Yeah, yes, and the minus has cancelled here. So let us make a change of variable, which is very natural here. All the functions depend only on the momentum scaled by thermal momentum. So this will be our change of variables. Xi is momentum scaled to thermal momentum. What we get as a result, G E squared divided by D KT, characteristic momentum thermal to the power of 2, 3, 5 to the 5th power divided by mass to the 2nd power, and the momentum relaxation time tau 0, and the remaining dimensionless integral is from 0 to infinity 4 pi xi to the power 4 plus alpha to 4 alpha delta xi exponent of minus xi exponent of Fermi level divided by kT and divided by 2ph cubed. Actually, this integral is tabular. It is cast into some gamma function. So let's denote this integral just as some function I. So what we got here is G E squared divided by, well, dimensionality is 3 by 3 kT, characteristic momentum to the 5th power divided by mass squared, tau 0, 4 pi divided by 2ph cubed, and the dimensionless integral here is xi to the power 4 plus alpha, the xi exponent minus xi, and the Fermi level. So to simplify this further, we should try to see whether there is something proportional to the carrier density. We need to factor the carrier density out. So the best way to do this is to write a separate, independent equation for the carrier density and try to collect everything that could be grouped into the expression for carrier density. The carrier density is spin degeneracy divided by 2ph cubed multiplied by the integral from 0 to infinity 4 pi momentum squared d pi divided by 2ph cubed multiplied by exponent So it is very much alike. So we can actually take the large blocks from this and to denote it as a carrier density. So let's try to group these large blocks. It is 4 pi g 2ph cubed. Again, we introduce characteristic momentum. The thermal momentum comes to the 3rd power here. We get this Fermi level exponent, and the dimensionless integral is from 0 to infinity xi squared delta xi exponent of minus xi. So we need to transform or to take all these blocks and group it into the definition of carrier density. Let me look onto my paper. I did it at home because we could be probably mistaken. Okay, so after we do all the maths, so after we pick all the terms that can be grouped into the carrier density, the final result that we will obtain will be, I'm afraid we don't have an eraser here, but let us just try to do it on the next slide. Oh. So what we got as intermediate results here, the conductivity was, we got that conductivity was equal to G E squared divided by 3 kT, 4 pi divided by 2ph cubed, thermal momentum to the 5th power mass squared, tau 0, and exponent of minus f divided by kT, and some dimensionless integral of the power 4 plus alpha, where I is psi. Yes, and for the carrier density, we got a remarkably similar expression. This was G multiplied by 4 pi 2 pi h cubed, p0 to the 3rd power, and the dimensionless integral was to the power of 2, and the same thermal exponent. Yes. So if we plug this into this, we will get a result for conductivity. It was equal to n e squared tau 0 divided by m and multiplied by 2/3 of dimensionless integral of the power 4 plus alpha divided by the dimensionless integral from the power of 2. So you see that the Drude formula is somehow deviated. It is not just the carrier density multiplied by charge square multiplied by momentum relaxation time divided by m, but there is some correction factor depending on the power to which the scattering rate depends on momentum. Well, this is quite natural. This is not unusual that in semiconductors it is, because the momentum relaxation time in Drude formula has to be somehow averaged. It should be averaged over the thermal distribution of electrons. And this numerical correction factor is just due to proper averaging of momentum relaxation time with respect to all electrons. Actually, there are some experiments that allow us to measure the momentum relaxation time from longitudinal conductivity and to measure the momentum relaxation time, for example, from Hall conductivity. And these expressions, according to theory, would be slightly different, and the difference would depend on the power alpha. Actually, measurements of these independent scattering rates allow us to guess what is the dominant scattering mechanism for the electrons and to guess the type of scattering that is dominant for this semiconductor. Now, do you have any questions to this part? I hope everybody of you would be able after this lecture to calculate the conductivity of some material, either metal or semiconductor, if you know the dependence of momentum relaxation time on momentum itself. Any questions?
Sorry, can I ask about previous part about metal?
Of course, but I hope it was not erased. Okay, just ask and I will rewrite it.
Okay. Here we have asked that velocity and tau is we can
Evaluate it at the Fermi level.
yes. And why we can't say the same about the density of states?
Well, we can say the same about the density of states, but you can say the same about the density of states and get the same result. I did it just for pedagogical purpose for you to see the carrier concentration explicitly, and it is when we retain the density of states, it is easier to see that the conductivity is proportional to carrier density. This is just pedagogically, but nothing would fundamentally change if you evaluate the density of states also at the Fermi level. Okay, if this was the last question, then I think we can pass to the next part of our lecture. The usefulness of our calculations was quite limited because we have assumed that the momentum relaxation time is proportional to the momentum itself to some power of alpha. But what is alpha and what is tau zero? How it can be related to the microscopics of scattering events? For example, if you know that the semiconductor is doped with impurities to some density Ni, can we calculate tau p explicitly? And this will be the goal of our next lecture, would be to show how momentum relaxation times can be calculated microscopically, just knowing how much the semiconductor or metal is filled with impurities. This will be the goal of the next 40 minutes. I hope we'll be okay for that. But on the next lecture, we'll be try to do the same for phonons. It will be much more complicated. So our goal will be to first to calculate the probability that an electron hitting an impurity would scatter in the final state characterized by momentum p prime. Actually, this is the problem very well known from quantum mechanics. We will use it, we will attack it with the Fermi golden rule, and then the result for scattering probability from Fermi golden rule would be placed into the collision integral and into the expression for momentum relaxation time. The potential that is created by a single charged impurity is the charge squared, because we assume that it is positively charged with the charge of that an impurity is positively charged with a charge of plus E plus elementary charge, and an electron also has the same charge. So the scattering potential is just E squared divided by the distance between classical position of electron and an impurity. The Fermi golden rule contains the scattering matrix element. So this is the matrix element of this scattering potential with respect to initial and final states. Initial and final states are plane waves in quantum mechanics. So these functions are just exponent to the momentum multiplied by radius and divided by the square root of volume. This is just to keep the dimensionality of we assume that the system is placed in some large but finite volume V. This is a general rule for quantum mechanics, and this is needed to keep all the dimensionalities correct. So we assume that it is all placed into the finite volume V. When we plug the explicit form of plane waves into this matrix element, we see a beautiful result that this matrix element is nothing but Fourier transform of scattering potential with respect to momentum. This is indeed the case, because here we have exponent of initial momentum multiplied by r, and here we have an exponent of minus final momentum divided by r. Grouping the exponents together would produce an exponent of initial minus final momentum for proper dimensional divided by h and multiplied by r, and integrated over all the space. But it is nothing but Fourier transform. This is the initial potential multiplied by exponent and integrated. And for this Fourier transform, we use the designation of f with the subscript q, where q is the transferred momentum during the collisions. The vector of q is the vector connecting the initial and final momentum. This is q. This is a very well-known result from quantum mechanics, and you can calculate this Fourier transform for this scattering potential. We actually did it when we considered screening in semiconductors. For three-dimensional Fourier transform, this is 4 pi elementary charge squared divided by transferred wave vector to the power of 2. And for two-dimensional situations, if we assume that r is lying only in the plane, then the result is different. It is 2 pi e squared divided by modulus of transferred momentum. You can calculate these integrals at home, and I hope you will cope with that. So the smaller is the transferred momentum, the higher is the scattering probability. It actually means that when hitting the charged impurity, the electron wants to be deflected only at small angles. The large angle scattering is not much preferred. Any questions here? Don't be shy. Okay. If yet no question, then we pass to further results. We would need to plug the expression for scattering matrix element squared into the Fermi golden rule and into the expression for the momentum relaxation time. Then, if we take the result from the previous board for U final initial, that it is 1 divided by volume of the system and multiplied by the Fourier transform of the scattering potential evaluated at momentum equal to pi minus pi prime, then we will get some, well, unnatural result. Let's focus on it before proceeding further. We would see that the scattering scattering amplitude is inversely proportional to the volume of the system, and the probability squared would be inversely proportional to the volume squared. When we integrate over the phase space, we get that with the fact that the volume here is in the first power. So all this stuff would be proportional to 1 divided by volume. And it is not a good situation in quantum mechanics. We usually got to the fact that the volume disappears from our calculation because it's an auxiliary quantity. Here we see that the scattering probability is inversely proportional to the volume of the crystal. And actually, when the crystal becomes very large, an electron cannot scatter the impurity. It looks like a paradox. Can anybody of you attempt to resolve it? There is no mathematical error. I suggest that there is no mathematical error in my calculations, but there is a conceptual error. Try to find it out. Why the scattering probability appears to be dependent inversely on volume of the system. Is it okay that the scattering probability for electron in the large crystal to hit one impurity to be inversely proportional to the volume of the system? It sounds okay. Actually, it is okay, because if we take a large crystal of volume V and place a random Yes, both answers are correct. Daria has noted that it is generally okay that we have a single impurity in the large volume, then the probability of scattering would be proportional to 1 divided by V, because the action radius of this impurity is finite, and electron as a plane wave is very, very large, but it can, in principle, pass through impurity and even not detect it, because it is single impurity in a very large crystal. But the physical statement of problem, as Maxim noted, should be different. The physical statement of problem is that crystal is doped with some amount of impurities with Yes, so we shouldn't work with one impurity in large volume. We should work with large number of impurities in large volume, so that the total number of impurities per volume is finite. And this is the impurity density. And I small have the dimensions of meters to the minus third power. It is the density of impurities, and so both total number of impurities tends to infinity and the volume tends to infinity, so that the density stays finite. This is a good statement of the problem from the physical point of view. So to calculate the momentum relaxation time properly, we should calculate the scattering not by a single impurity, but by an ensemble of impurities located at random positions. It sounds complicated, but it is actually doable. It's actually doable, and let's do this. So yes, what we have considered previously is a sample with one impurity, but this is not a good statement of the problem. Let's consider a sample with positively charged impurities at random positions, R1, R2, R3, R4, R5, and so on. And let's try to figure out the scattering probability in Fermi golden rule in the same approximations with this ensemble. In this approximation, the potentials of impurities are additive. So this is the additivity of electric forces. Electric potential created by an ensemble of impurities is the sum over random positions characterized by subscript I of column potential U0 reckoned from the point Ri. Now we remember, so according to the previous result, the scattering matrix element would be the Fourier transform of this net impurity potential with respect to the transferred momentum. But Fourier transform is a linear operation, so the result would be the sum of Fourier transform of individual potentials created by each single impurity. Here we should remember the following knowledge from the Fourier analysis. I hope you know it. If the Fourier transform of function f on x is f is denoted by f cubed, what would be the Fourier transform of shifted function f on x minus f0? Do you remember this theorem or general statement?
The Fourier transform should be multiplied by exponent of I q f0.
Yes. This is easily proved by a change of variables and by the definition of Fourier transform. To take a Fourier transform of shifted function, we should take the Fourier transform of original function and multiply it by the phase factor of q, the transferred momentum, and multiply by x0, which is the value of shift in coordinate space. We do this to calculate the Fourier transform for an impurity located at point Ri. This is the Fourier transform of impurity located at the origin of coordinate system, and I denote it as fq of u0, and multiplied by a phase factor of eqri, where Ri is the random position of the random impurity. And now we should take this sum, which contains a very large number of terms, and to plug it and to take its modulus squared. The modulus squared now contains double sum over where I and G are the indices running over all the impurity positions from 1 to the number of impurities, both for E and G. What we get here is the Fourier transform of individual impurity squared and multiplied by a phase factor of IQ RE minus RG, where RE and RG are two positions of impurities. So here we have totally an I squared terms. This is actually a very large number of terms in this sum, but not each of them are important. Let's try to arrange these terms into a matrix. So let's let index I will be along the columns and index G will be along the rows. First impurity, second, third, la la la, nth. First, second, nth. There are terms where I equals to G, and these terms are just Fourier transforms of bare impurity potential squared. These terms will be along the diagonal. F u0 squared and so on. And there are off-diagonal terms which are the same, but they contain some random phase factors. Let's consider some off-diagonal term, f u0 squared by exponent of iq r1 minus rn. And there is some other term, f u0 squared exponent of iq r, for example, 3 minus r5. Actually, when we take the sum of all elements of this matrix, the elements on the diagonal will be positive, and they will be all positive and all the same. But the terms of the diagonal will mainly cancel, because, for example, this phase can be positive and this phase can be negative, because the positions of impurities are really random. For example, for each matrix element in the top right side of the matrix, we will get the matrix element in the bottom lower side of the matrix with the opposite phase. So they will not cancel exactly, but they will cancel to the leading order in the carrier density. So our approximation is to sum only the diagonal matrix elements, and the number of these diagonal elements is the same as the number of impurities Ni, and you see that a good quantity of Ni divided by V has appeared in our result. There is one more inverse volume, which will be, however, cancelled upon summation in the phase space. So what we did, we have linked the total scattering probability to the density of impurities, and to a very good extent it contains only the diagonal matrix elements with constant sign. After we do that, we plug this expression into the momentum relaxation time, and we get a result that is ready for further computations. It is integral over momentum space divided by 2ph to the power of sample dimension, 2ph from the Fermi-Golden rule, scattering by individual impurity, and here the density of impurities is the total number of impurities divided by volume, delta function for energy conservation, and the transport cosine. Now we can take Fourier transform both for three-dimensional situations and for two-dimensional situations and make the result ready for computation. Minus pi squared modulus for 2D. How much time do we have left? Oh, we have 15 more minutes. So I hope we will be able to get the result up to the end. If P is momentum but not the wave vector, then we should write extra factor of h here. So our final goal would be to evaluate the emerging integrals and find the momentum relaxation time as a function of carrier density. I will focus on a two-dimensional electron system with a parabolic band dispersion when energy versus momentum is p squared divided by 2m. This is relevant to inversion layers in silicon, and this is relevant to classical heterostructures like in gallium arsenide, but it would be slightly different from the case of graphene. So the case of graphene could be a good home task for you. So let's evaluate the remaining integrals, and in meanwhile we will handle this pathological delta function and show that the answer is okay from the physical point of view. So the initial expression, to make it ready for computation, we write the momentum space in polar coordinates explicitly, p prime delta p prime divided by 2ph squared. This is the Fermi-Golden rule. This is 1 minus cosine of scattering angle. The trick that we are going to do here. Можно, пожалуйста, камеру чуть поближе на доску, тут будут формулы, а меня можно не фокусировать. Let us focus the camera closer because the equations are more important than my face here in this situation. So we will need some auxiliary stuff. We would be willing to get rid of the delta function of energy. So it is good to express the momentum, delta momentum, through the energy. You can do it very easily because just differentiating the expression E equals p squared divided by 2m, you get the beautiful fact that momentum, delta momentum is the mass multiplied by delta energy. And this delta energy can be used to integrate this energy conservation explicitly. So we will need finally to integrate only over the angles. Good. The first trick is to integrate the energy, and it can be done. I use this notation to integrate over the energies. And the only integral that I have remained here is the angular integral from 0 to 2 pi of the sine squared of theta divided by 2 comes from the scattering probability, and 1 minus cosine theta comes from the fact that small angle events do not contribute to transport. I use the following simplification that 1 minus cosine theta is exactly cancel the denominator, and the integral over the angles is nothing but 4 pi. And this is already our final result. We have easily integrated the energy dependence exactly, and we have easily integrated the angular dependence of scattering probability. The inverse relaxation time is proportional to the impurity density, fourth power of elementary charge, reduced Planck's constant. Actually, this is the technical fault here. Everywhere H is a reduced Planck's constant. Okay, I didn't tell it. Actually, kappa is the background dielectric constant. Everywhere in our previous notations, we have treated scattering potential as bare scattering potential. But if impurities are immersed into the medium with dielectric constant kappa, then it should be replaced to kappa R. So kappa is the background dielectric constant. Dielectric constant. For example, if it is an inversion layer in silicon, then we should write the dielectric constant of silicon, kappa silicon equals to 12. Roughly the same holds for gallium arsenide. This accounts for screening of column impurity by the lattice. And E is the energy of electron. Energy of electron. How energy has appeared here? This is because the scattering probability is inversely proportional to the transferred momentum. Actually, I didn't comment on one point here, why this factor has appeared here. What is 2 pi sine of scattering angle? Yes, of course. This is just geometry. This is pi minus pi prime. Initial momentum of electron equals pi. Final momentum of electron equals pi prime after the scattering. And it scatters by an angle of theta. And this line is nothing but transferred momentum. But this is now a school geometry. This is triangle with equal sides, and this is the bottom of this triangle. then Q equals 2 pi sine of theta divided by 2, because this is nothing but theta divided by 2. The column scattering amplitude into D is inversely proportional to transferred momentum, and the transferred momentum can be found from simple geometry. The sides are equal here because the scattering is elastic. The modulus of momentum doesn't change. It is possible to write it down up to an end, because this is not, it doesn't look very good from the sense of dimensionality. You don't explicitly see that this has the dimensionality of inverse seconds. To do this, I would try to merge this elementary charge and kappa and so on into the Rydberg constant. Rydberg constant is the binding energy in the hydrogen atom. And I have done it at home, and you can try to do this also. This is pi of density of multiplied by density of impurities divided by density of electrons multiplied by the ratio of Fermi energy to the energy, where EF is the Fermi energy into D, and multiplied by the Rydberg energy divided by H. The Rydberg energy is actually modified here by the presence of dielectric constant. Rydberg is m e to the 4th power divided by 2 h squared kappa squared. This is the modified Rydberg for the semiconductor. It differs from Rydberg in hydrogen theory because here we have screening to the 2nd power, and frankly speaking, here we have effective mass, not the bare electron mass. So this Rydberg is generally by 100 times smaller than Rydberg in hydrogen theory, but the dimensionality is the same. So what we got? The dimensionality is correct. This should have the dimensionality of frequency. Energy divided by Planck's constant is frequency. And there is extra small factor, the density of impurities divided by density of 2D electrons. Typically, when we dome the two-dimensional system, the number of impurities is quite little and the number of electrons is quite large, so that this factor is well below unity. So, actually, this brings me to the end of the lecture. I hope that the transport theory that we have developed has taught you how to calculate the scattering times and collision frequencies in 2D and 3D systems microscopically. Now, once you know the density of doping impurities, you can calculate the momentum relaxation time in any semiconductor and also its mobility. I have done it at home. Just let's look at some plots. Let's look at some plots, how it works in action. This is the calculated scattering rate or the collision frequency between electrons and impurities versus electron density in a two-dimensional system at different impurity densities, from 10 to the 10th units per centimeter squared to 10 to the 12th units per centimeter squared. The momentum relaxation time at these impurity densities can range from 10 to minus 13 seconds, 100 femtoseconds, to 10 femtoseconds and to 1 femtoseconds. The higher is the electron density, the more rare are the scattering events. This is quite natural because we have higher density of electrons, higher average energy, and faster particles. If the particles are fast, they can pass near the charged impurities without noticing them, and therefore higher doping means smaller scattering rate in two-dimensional electronic systems. Actually, we can link the scattering rate to mobility using the known formula that mobility is elementary charge multiplied by momentum relaxation time divided by mass, and this result is shown on the next slide of my talk. This is the mobility of electrons in two-dimensional system in centimeters squared per volt per second versus electron density. The higher is the electron density, the higher is the mobility. This is the so-called impurity limited mobility. So normal mobility in semiconductors is 1000 centimeters squared per volt per second. This is the room temperature mobility in silicon. 1 million is a huge mobility. You can observe many exotic quantum phenomena if you have a mobility of 1 million. And this is achievable, but it is achievable at relatively high electron density and at very small doping density. Actually, to achieve this, you need also to cool the sample down to get rid of phonons, because not only impurities but also lattice vibrations contribute to mobility. How to calculate this contribution due to phonons would be the subject of the next lecture, the next week. But now the take-home message is that calculation of mobilities and scattering times with known density of impurities is a doable and actually a simple task. Any questions from you? Don't be shy. Okay, if no question, then I would like to ask you to repeat what are phonons to the next lectures, and what are phonons, what is their dispersion, how they are linked to the sound in crystals, and some of these topics from the general physics. And we will take an advanced view from the points of quantum mechanics and physical kinetics. Thank you for attention and goodbye.